Alright, this is the 12.5 video. If you're wondering what happened to the 12.4 video, there wasn't one because we don't do 12.4. So we are skipping ahead to 12.5. In 12.5, there are several things. There's this N vector, this B vector, there's some special kind of planes, there's tangential and normal components, there's all kinds of stuff. So we're going to start here. This is page 674. And it gives you some information here. I've highlighted it so you can go back and read it on your own. But it's got the unit tangent vector, that capital T, which we saw before. That was the velocity vector divided by its magnitude. And then you've got a unit normal vector, which we'll talk about in just a second. And then you've got a binormal vector. So the binormal vector is the cross product between the unit tangent vector and the unit normal vector. So the unit normal vector, here, this was actually in 12.4. 12.4, it had curvature and normal vectors. So we don't do curvature for whatever reason. The calculus coordinator decides these things. But we do normal vectors, so, you know, whatever. So anyway, here it is. This is page 670. This is the formula for the normal vector. So notice the normal vector, first of all, is, it's the unit normal vector. It's a unit vector. It's taking a vector and dividing by its magnitude. So whenever you take a vector and divide by its magnitude, it makes it a unit vector, magnitude 1. But then what it is it's, if you've already found your t vector, which remember was this we just talked about, it's the derivative of the t vector with respect to t, because it's a function of t, and then divided by its magnitude. So just like the v vector is the derivative of the r, so this is the derivative of r over the magnitude of the derivative of r. This is the derivative of t over the magnitude of the derivative of t. Okay, so that's on page 670. So flipping back over here, we know what a tangent vector is. Tangent vectors are vectors that are tangent to the curve, obviously. But the unit normal vector, it gives you, here it says the direction in which your path is turning. So it's kind of showing you how you're turning. And then, I don't know if you can see this with that glare, but the tendency of your motion to twist out of the plane is given by this binormal vector. So these are like for movements. So what they create are these little frames. I don't know if you can see them very well. Green, blue, red vectors. And so this is the frame. They are, it says here, mutually orthogonal, which means they're each orthogonal to each other. All right, and then here it's telling you because B is the cross product of t and n, then it's orthogonal both to t and to n. And here it's talking about that vector frame, and they call it the TNB frame because it's made up of the unit tangent, unit normal, and binormal vectors. Okay, so page 675. Here's all the work for it. We're not really, because this video is already going to be really long by itself, so we're not going to go through this, but here's the work for it so you can see. Anytime you see this K, this is curvature. This is, again, one of those things for whatever reason the calculus coordinator decides we don't do, so it makes this a little hard to talk about. But anyway, this is the development of where the tangential and normal components of acceleration come from. So what you have, if you look at this vector, this is kind of making sense of what we're doing. You have your curve, it's blue. You have your acceleration vector. Notice this is the acceleration vector. It's not a tangent vector, so it's not tangent to the curve, but this acceleration vector. And then if you break this down into, here's the unit tangent vector, so that is tangent to the curve, and the unit normal vector, then what you have is the part of the acceleration vector that's here with the unit tangent vector, that would be the tangential component of the acceleration. And then the part that's over here with the normal vector, that would be the normal component of acceleration. So what you're doing, if you look at it here computationally, you are breaking the acceleration vector down into two parts, and you have the part in the direction of the tangent vector and the part in the direction of the normal vector. So here's the formula for the a sub t. You can think about it either as the second derivative of the position function s, or you can think about it as the derivative of the speed. Notice this is the magnitude of the velocity vector, so it's speed, so the derivative of the speed. And then, where is it? Oh, down here. Here's the formula for the normal component of acceleration. Notice the tangential component and the normal component, they are not vectors. They're scalar quantities because they are not vectors. So you have the acceleration vector, and then here you have its magnitude squared minus the tangential component squared, take the square root. Okay, so this is, and they tell you here where it comes from. This is that same thing. It comes from solving this equation for a sub n. All right, so there's some more information. I'm not going to read this to you again because this video is already going to be so long. But there's some more information here. This is page 675. Here and here and here. So if you kind of see, oh well, and then all of this stuff too. I guess I got tired of highlighting and just started underlining. Basically just read all of page 675. That would be easier. All this stuff in between the boxes. Read everything in between the boxes on page 675. Okay, so you can pause the video and read it now, or you can write yourself a note to go back and read it later. But it's just some more information on what we're doing. Okay, now let's look at these planes. This is page 677. Page 677, these were those three vectors that we were just talking about, and this is that T and B frame that they create. And so if you look at, like, for instance, this plane is formed by the T vector and the B vector. That's called the rectifying plane. Then the normal plane is formed by the normal vector and the binormal vector. And then the oscillating plane is formed by the tangent vector and the normal vector. Okay, so these are those three planes that are formed. And then they have here, and we don't use all of these formulas, but a summary kind of the formulas that we've talked about. So the unit tangent vector, remember that was from a previous section. This is from 12.4. This is from this section. We're not doing curvature or torsion. I don't know. We're not doing either one of those. And then here's the tangential and normal components. So you do not write this one. This one is using curvature, and we don't do curvature. So don't write this one. Write this one instead. So this is the one that you want to use. So in my notes, I have the information about the tangential and normal components. And so I do have this one in my notes just because when I made my notes, I thought we were doing curvature, and we're not. And so do not write that one. That was, by the time I wrote it, I realized we were omitting curvature. So we have this one that we're using instead. I just didn't want to have to white out everything. So here, a sub t and a sub n are scalar quantities, meaning not vectors. It doesn't mean they're constants. So they typically are functions of t, but they are not vectors. And then this is one of those pictures we already looked at. And these are the three planes. And so remember, I didn't show you this in the picture, but remember when we talked about planes in 11.5, to have a plane, you have to have a point in the plane and a vector orthogonal to the plane. And so, like for instance, on the oscillating plane, it's formed by t and n. So B would be normal to the plane. And then for the normal plane, T is normal to it. For the rectifying plane, N is normal to it. So I'll show you in the picture. You have this point P. Notice that point P, it's on all three vectors. So you can use that point for all three of your planes. And then like here, if you're in the oscillating plane, for instance, see how in the oscillating plane, the B vector is orthogonal to the plane? Or here in the rectifying plane, see how the N is orthogonal. So that's what you're going to use for those lowercase n vectors that you needed for the formula for the plane. Okay, so let's look at some problems. 1 and 2, well, 1 and 2 and 3 through 6. I don't know why they separated those up. Oh, I see. These, they didn't give you t values to plug in, and here they did. Okay, so in both cases, you're trying to break down the acceleration vector into its components, the tangential and normal components, and then in this one, you're actually plugging in numbers. Okay, so let's try some of these. All right, I had to plug in my phone because it was about to die, so I keep having to pull on the cord. Stupid cord keeps getting in my way. But it's better than my battery dying halfway through this video and having to do it in 2 parts. So I will put up with the cord, even though it's getting in my way. Okay, obviously first is number 2. And so this is the one that they did not give us the t value for. So they start with giving us this r. This is the position vector. So you find the velocity, which is the derivative. Then you find the magnitude of the velocity, which is the speed. And then the tangential component, that's what this a sub t, the tangential component of the acceleration. It's the derivative of the speed. So you go back up here to the speed. The speed can be a constant, or it's usually a function of t. Here it happens to be a constant. So if it's a constant, when you take the derivative of it, obviously you're going to get 0. And then the acceleration vector is the derivative of the velocity vector. This one's a boring example, but the velocity vector, all of its component functions were constants. And so when you take the derivative, you get a bunch of zeros. So obviously the magnitude of that, I showed the work, but it's 0. And so the normal component of the acceleration vector is the magnitude of the acceleration vector squared minus the tangential component squared. So notice both of those were 0, so that's just 0 for that. Sorry, I pointed to the wrong thing for that. But then the acceleration vector is a vector, and so it's 0 here times the t vector plus 0 here times the n vector. So notice it's 0, the vector. If you write that without a hat, it's wrong, because 0 without a hat, that's a number. 0 with a hat, that's a vector. Two totally different things. Okay, so it's extremely, extremely important that you put hats on your vectors. A lot of you are still losing points for that, and you're going to keep losing points for that all semester. If it doesn't have a hat on it, it's not a vector. Well, unless it's in your book, and then it's bold, and that's the same thing as a hat, but you can't really do that unless you're typing, so I'm talking about for writing. All right, let's look at another one. This one's the same thing, but they give you a t value to plug in. This is number 4. So we're going to do the same things. We're going to find the velocity vector, which is just the derivative. So notice here and here, it's product rule. You have to do product rule. Okay, so product rule, I end up with 2 pieces. Then I have to find the magnitude. So notice here I have to FOIL. Here I have to FOIL. So I end up with bunches of pieces. But I can, these two, cosine squared plus sine squared is just 1. And then from this one and this one, I can factor out a t squared, and then I have another sine squared plus cosine squared, which is also a 1. And then I can do t squared plus 4t squared, which is 1 plus 5t squared. All right, so the tangential component of acceleration is the derivative of the speed. So this was the speed. When I take the derivative of it, it's chain rule. So here's my outer derivative. Here's my inner derivative. Simplifies to this. So that's my tangential component. And then now for my normal component, I need to find the acceleration. So for the acceleration, you're taking the derivative of the velocity. Notice this piece needs product rule, and this piece needs product rule. And then for this piece, you have to distribute that negative to both pieces of the product rule. So see how both of these are negative now? And so this would be my simplified version of the derivative. And then here, okay, let me just explain this real quick. At this point, you can either go ahead and find the magnitude of this and then go from there. Or because I'm going to have to plug in, hold on, I can't, I have to scoot the book over because of my stupid cord. They told you t was 0. Or to make your work easier, you can go ahead and plug in the 0, because at this point you're done taking derivatives. This was the last derivative you had to take. You couldn't do it up here because, well, like you couldn't plug it in for 0 here, because you were still going to have to do, or here, either one of those, you couldn't plug in the 0 yet because you were still going to have to do another derivative. Here for this one, or up here, you're going to have to do the derivative to get the a. So if you still have more derivatives to take, you cannot plug in constants, because then you would have a constant, and then the derivative would be 0. And so if you are not done taking derivatives, you cannot plug in numbers yet. But once I got this, I'm finished taking derivatives, and so I can go ahead and plug in my number, because it's easier to work with numbers than functions. Okay, so that's why I went ahead and plugged in the 0 here before continuing, but I didn't plug in the 0 here. So you cannot plug in for t until you're finished taking derivatives. All right, so that was my acceleration vector at t equals 0. So now I'm going to find the magnitude of it, and it's the square root of 8. So for my normal component of the acceleration vector, I plug in this, which is the square root of 8. I plug in this, which I found, where did I do that? Oh, I didn't even show that. I totally skipped that step. Here was my, sorry, I did it. I didn't show it to you. Here was my a sub t, and I just stopped there. But now I plug in the 0 into that answer. So a sub t at t equals 0, that ended up being 0. So that's where did it go? There. That's where this 0, nope, that's where this 0 comes from. That's where I was. That's where this 0 comes from. So this is my normal component. And so as a vector, the tangential component was 0. The normal component was this, and so it simplifies down to just this, which the acceleration vector obviously is a vector, so make sure you write it as a vector. Okay, so hopefully that makes sense about when to plug in the numbers and when not to. All right, Number 8, different set of directions. Hold on. So here, find R, T, N, and B at the given value for T, and then find the equations for the oscillating, normal, and rectifying planes. So here they already gave you the R, but they want you to find the R at the T. And so that one's easy. But then T, N, and B take some work, and then you've got to find 3 planes. So you're really looking at 7 answers here. So make sure you do it all. This is going to be a long one. That's okay, though. All right. Here's the R. So here's my R of 0, which is just I. Set that aside. I can't use that anymore because I've already plugged in a number into it. So here would be my, I'm going back to my R here. I need for my capital T, I need my velocity vector first. So go back up here. Don't use this because I've already plugged in a number, and that's not okay to use that if I'm going to have to take a derivative, because that's just going to give me 0. So go back up here, pretend like I haven't plugged in yet. Go back up here and find the velocity vector, which is just the derivative. So that's this. This is the derivative of that R. And then you're going to do the magnitude of it. Don't plug in the 0 yet because you got to take a derivative. Oh, wait, just kidding. No, I was thinking tangential components. You're not doing the tangential component, so you could have gone ahead and plugged in the 0. Oh, no, wait, except you need it for the N. Sorry. I've been watching football all day. My brain is totally fried because after watching all of these blowout games, it's just, I don't know, my brain's kind of melted. It's like these scores are ridiculous. Like the Arkansas score, like 70-something. What is that about? I don't even know. So I think if you summed up the whole day's worth of football games in the SEC today, it would sum up to the word blowout because they've been crazy. Okay, so sorry, my brain's not really working because it's late Saturday night. I'm tired. But so for here, you are going to need to take the derivative of the t, so you're going to need it as functions of t. Okay, so here was my v vector. Here's my magnitude of my v vector, which notice it was originally a function of t, but then because sine squared and cosine squared are 1, it ends up being just a constant. And so my capital T, I take the velocity vector, put it on top, magnitude, put it on bottom, and it's this. And then I want to plug in the 0. So plugging in the 0 simplifies down to this. All right, but for the n, you can't use this one where you've plugged in the 0 because you're not supposed to plug in numbers if you still need to take derivatives. I was just doing this so that all my answers were kind of in order. But I need to go back up here to before I plugged in the 0. So anytime you have to take derivatives, go to where you haven't plugged in numbers because you can't have numbers plugged in when you're going to take derivatives. So going back up here to this one, that's what I'm taking the derivative of. So since this is our first n one, again, you're going back to the t before you plugged in the number. You're taking the derivative of it with respect to t. That's this part. So I get this. Okay, and then I'm going to do the magnitude of that. And I get this. But then when I factor out the 1/2, cosine squared plus sine squared is 1. So I get this. Okay, so that's my, this, where did it go? Here. This is my derivative. This is my magnitude of the derivative. So I take the derivative, put it on top, magnitude, put it on bottom, simplifies down to this. Now I'm going to plug in my 0, and so this would be my n vector. All right, now I need the t vector and the n vector to find the b. So I have those two. Okay. And then over here, I have papers everywhere. Hold on, put them back in order. There we go. Okay, so for the b vector, it's the cross product between the t and the n. So the order matters on cross products. You're going to get the wrong signs if you do it backwards. So this one, the t has to be first and then the n. So this is the t, this is the n. I do the cross product and it ends up with this. And notice because I used the t with the 0 plugged in and the n with the 0 plugged in, this already comes out as the b with the 0 plugged in. And another thing, well, never mind, I'll show you that later. Okay, let's go. I forgot we had to do still to do the planes. Okay, let's look at the oscillating plane. So the oscillating plane was formed by the t and n, and so the orthogonal vector is the b. So that's what I'm using for my lowercase n. So here's my b. And then the point, we talked about this before in a previous section, I can't remember which one, but the point corresponds to the terminal point of the position vector at the value for t. So my t value here is 0. So if I plug 0 in, I get this vector, and so the terminal point of that vector is this, and so that's going to be my point for all three planes. I'm going to use the same point for all three planes. Okay, so the equation for a plane is an 11.5. You can look it up. It has the ends out here is the coefficients, and the point in here is the numbers you're subtracting. And then this answer is okay, but notice if you multiply both sides by negative square root of 2, this one looks a whole lot better. So this one wouldn't have been wrong. This one is just better. Okay, so for the normal plane, it's the plane formed by the n and b vectors. So the t vector is the one that's orthogonal to the plane. So here's my t vector. I'm using that as my lowercase n. Here's my same point. I'm going to use that point for all three planes. So here's my equation. Again, if I multiply both sides by the square root of 2, it looks much nicer. And then lastly, the rectifying plane. The capital N is the normal vector, so that's what I'm using for my lowercase n. Again, still the same point. And this one's really nice. So those are my three planes. All right, last problem, which is a good thing because my throat is starting to hurt. And I haven't even been screaming. I don't know why my throat hurts. You would think I'd been screaming at all the football games I've been watching, but they haven't been worth screaming about. So pretty much no screaming going on today, which I'm sure my family is very happy about. Okay, 9 to 16. Oh, that's talking about 12.4. Now it's saying, okay, we're not doing this, that torsion. I don't know if I'm saying that right, but whatever, you know what I'm talking about. We're not doing that, so it's just the B. So we're not doing curvature either. So those two we're not doing. But here it says in 12.4 you found T and N. You really didn't, because we didn't do 12.4. So while it looks like here all you have to do is find the B, you have to find the T and the N because that's what the B comes from. So you're actually doing all three things here. So sorry. Number 12 is here. This is our last problem, if that makes you feel better. All right, so number 12. Since we've already done, don't look at my work. Don't look. Okay, number 12. Since we've already done one of these already, I'm going to have you try this by yourself. So here's what I want you to do. I want you to pause the video. Wait till I'm done talking though. Hold on. Don't pause it yet. Okay, in a minute, I'm going to have you pause the video, and I want you to try it by yourself. And then when you're done, unpause the video, and then you can watch it and see if you got it right or not. And that way you'll see whether you're understanding this or not. Okay, so now for real, pause the video and try this by yourself. All right, so hopefully you actually paused the video and tried this. If you didn't, shame on you. I saw you. Just kidding. That's kind of creeperish. I don't stalk anybody. That would be weird. Okay, here would be my problem that I was given. My velocity vector is the derivative, and then I'm finding the magnitude of that. Again, this cosine squared plus sine squared comes up all the time, and so that's why it is becoming constants, but normally they're functions of t. It's just I keep having these sine squared plus cosine squared identities. Okay, so the capital T vector, I just stack, sorry, excuse me, keep yawning, the V vector on top, the magnitude on the bottom, break it up into pieces so it looks better. This would be my T vector. For my N vector, I need the derivative of that and its magnitude. So here's the derivative of that. Here's the magnitude, terrible numbers. If I put this one on, or something like this one on the quiz, I would change the numbers and make it nicer. If you have something like this in the homework, I can't remember if they're bad numbers in the homework or not, but if they're bad numbers in the homework and I pick that problem for the quiz, I'll change the numbers and make them nice. So I wouldn't expect you to, off the top of your head, know what the square root of 576 is. I didn't know that, but anyway, that's the derivative and the magnitude. So you stack the derivative and the magnitude. And then when you simplify, this one simplifies down very nicely to just this. And notice here they didn't give you a value for t to plug in, and so you're having to do these as functions of t. So for your b, it's the t on the top, the n on the bottom, and so you're doing the cross product. Hopefully you can see that. And so this is the answer that you should have ended up with for your b. All right, so hopefully you got that right, and hopefully this stuff makes sense. Notice there's, hold on, keep having to slide everything around because of this cord. Let me find them, hold on. Okay, so, no, that's not the one I was looking for. Okay, I don't know where the example was I was going to show you. I guess there's not. I was going to say there's some examples, but there's just that one, and that one's not. That one's okay, but that one's not great. So, sorry, you just have the ones I did in the video to look at. So, anyway, that is all from both 12.5 and chapter 12. So if you look on page 683 and 684, there's some problems that you can do in the practice exercises if you need more practice. So for the problems here, anytime they ask you, like here's some of these with the ones that you were just doing. Anytime they ask you for curvature, like here, just ignore that because we didn't do curvature, and same with torsion. You can just ignore that as well. So, all right, well, if you have any questions, just send me an email.